Chapter 2: Data Models and Query Languages. The limit of my language mean the limits of my word. Ludwig Wittgenstein, Tractatus Logic Philosophicus, 1922. Data models are perhaps the most important part of the developing software because they have such a profound effect not only on how the software is written, but also on how we think about the problems that we are solving. Most applications are built by layering one data model on top of another. For each layer, the key question is how is it represented in terms of the next lower layer? For example, as an application developer, you'd look at the real world in which there are people, organizations, good actions, money flows, sensors, etc. A model it in terms of objects or data structures. An API that manipulates those structures are often specific to your application. When you want to store those data structures, you express them in terms of general purpose data models, such as JSON or XML document, tables in a relational database or a graph model. 3. The engineer who built your database software decide on a way of representing the JSON XML relational graph data in terms of bytes and memories on this or in a network. The representation may allow the data to be queried, searched, manipulated, and processed in various ways. At lower levels, hardware engineers have figured out how to represent bytes in terms of electrical currents, pulse of light, magnetic fields, and more. In a complex application, there may be more intermediary levels, such as APIs built upon APIs, but the basic idea is still the same. Each layer hides the complexity of the layer below by its providing a clear data model. These abstractions allow different groups of people, for example, the engineers of the database vendor and the application developer using their database to work together effectively. There are many different kinds of data models, and every data model embodies assumptions about how it is going to be used. Some kind of usage are easy and some are not support. Some operation are fast and some perform badly. Some data transformation feel natural and some are awkward. It can take a lot of effort to master just one data model. Think how many books there are on relational data modeling. Building software is hard enough, even when working with just one data model and without worrying about its inner working. But since the data model has such a profound effect on what the software above it can and cannot do, it's important to choose one that is appropriate to the application. In this chapter, we will look at the ranges of general purpose data models for data storage and querying, going to in the preceding list. In particular, we will compare the relational models, documents model, and a few graph-based data models. We will also look at various query languages and compare their use cases. In chapter 3, we will discuss how the storage engine works, that is, how these data models are actually implemented. Point 3 in the list. Relational model versus document models. The best known data models today is probably that of SQL, based on the relational model proposed by Edgar Code in 1970s. Data is organized into relations, called tables, in SQL, where each relation is an unordered collection of tuples, rows in SQL. The relational model was a theoretical proposal, and many people at the time doubted whether it could be implemented efficiently. However, by the mid 1980s, relational databases management and SQL have become the tool of choice for most people who need to store and query data with some kind of regular structure. The dominance of relational databases has lasted around 25-30 years, an eternity in computing history. The roots of relational database lies in the business data process, which was performed on a mainframe computers in 1960 and 70s. The use case appeared mundane from today's perspective, typically transaction processing, entering sales of banking transactions, airline reservations, stock keeping in warehouse, and batch processing, customer invoicing, payroll reporting. Other databases at that time forced application developers to think a lot about the internal representation of the data in the database. The goal of the relational model was too high. That implementation needed behind of cleaner interface. Over the years, there have been many competing approaches to data storage and query. In 1970s and early 1980s, the network model and the hierarchical model were the main alternatives, but the relational model came to dominate them. Object databases came and went again in the late 1980s and early 1990s. XML databases appeared in the early 2000s, but have only seen niches adoption. Each competitor to the relational model generates a lot of hype in its time, but it never lasts. As computers became vastly more powerful and networked, they started being used for increasingly diverse purposes. And remarkably, relational databases turned out to generalize very well, beyond the original scope of business data processing to a broad variety of use cases. Much of what you see on the web today is still powered by relational databases. Be it online publishing, discussion, social networking, e-commerce, games, software as a service, productivity application, or much more. The birth of NoSQL. Now, in 2010, NoSQL is the latest attempt to overthrow the relational model's dominance. The name NoSQL is unfortunate since it doesn't actually refer to any particular technology. It was originally intended simply as a catchy Twitter hashtag for a met on open source. Distributed non-relational databases in 1999. In 2009. Nevertheless, the term struck a nerve and it quickly spread through the web, start to communicate community and beyond. A number of interesting databases tips that are now associated with the NoSQL hashtag, and it has been retroactively reinterpreted as no only SQL. There are several driving forces behind the adoption of NoSQL databases, including a need for greater scalability that relational databases can easily achieve, including very large databases with very high write throughput. A widespread preference for free and open source software over commercial database products, especially as a query operation that are not well supported by the relational model. Frustration with the restrictiveness of relational schemas and a desire for a more dynamic and expressive data model. Different applications have different requirements. The best choice of technology for one use case may well be different for the best choice for another use case. It therefore seems likely that in the foreseeable future, relational databases will continue to be used alongside a broad variety of non-relational data stores, an idea that is sometimes called polyglot persistence. The object relational mismatch. Most application development today is done in object-oriented programming languages, which lead to a common criticism of the SQL data model. If data is stored in relational database, and our translation layer is required between the objects in the application code and the database model of table, rows and columns, the disconnect between the models is sometimes called an impedance mismatch. Object relational mapping frameworks like Active Record and Hibernate reduce the amount of boilerplate code required for these translation layers, so they can completely hide the difference between the two models. For example, Figure 2.1 illustrates how resume, a linked profile, could be expressing a relational schema. Profile as a whole can be identified by a unique identifier user ID, fields like first name and last name appear exactly once per user, so they can be modeled as a column on the user tables. However, most people have had more than one job in their career positions, and people may have very number of periods of dedication and any number of pieces of contact information. There is one-to-many relationship from the user to these items, which can be represented in various ways. In the traditional SQL model, prior to SQL 1999, the most common normalized representation is to put positions, education, and contact information in a separate table with a foreign key reference to the user table, as in Figure 2.1. Later version of the SQL standard added support for structured data types, and XML data. These allow multi-value data to be stored within a single row, with support for querying and indexing inside those documents. These features are supported to varying degrees by Oracle, IBM, DB2, MS SQL Server, and PostgreSQL 6 and 7. A JSON data type is also supported by several databases, including IBM, DB2, MySQL, and PostgreSQL. A third option is to encode jobs, education, and contact info as a JSON or XML document, store it as a text column in a database, and let the application interpret its structure and content. In this setup, you typically cannot use the database to query for values inside the encoded column. For a data structure like a resume, which is mostly a self-contained document, a JSON representation can be quite appropriate. Example 2.1. JSON has the appeal of being much simpler than XML. Document-oriented databases like MongoDB, RethinkDB, CouchDB, and Express support these data models. Some developers feel that the JSON model reduces the dependence between the application code and the storage layer. However, as we shall see in Chapter 4, there are also problems with JSON as data encoding format. The lack of a schema is often cited as the advantage. We will discuss this in the schema flexibility in the document model on page 39. The JSON representation has better locality than the multi-table schema in figure 2.1. If you want to fetch a profile in a relational example, you need to either perform multiple queries, query each table by user ID, or perform a messy multi-way join between the user tables and its subordinate tables. In the JSON representation, all the relevant information is in one place and one query is sufficient. The one-to-many relationship from the user profile to the user positions, educational story, and content information imply a tree structure in the data, and the JSON representation makes this tree structure explicit. See figure 2.2. Many-to-many and many-to-many relationship. Many-to-one and many-to-many relationship. In example 2.1, in the preceding section, region ID and industry ID are given as IDs, not as a plain text strings. Greater, Zero, Arena, and Philanthropy. Why? If their user interface has free text fields for entering the region and the industry, it makes sense to store them as a plain text strings. But there are advantages to having a standardized list of geographic regions and industries, and letting users choose from a drop-down list or autocompleter. Consistent style and spelling across profile, avoiding ambiguity if there are several cities with the same name. Ease of updating, the name is stored in only one place, so it is easy to update across the board if it ever needs to be changed. Change of a city name due to a political event, for example. Localization support, when the site is translated into other languages, the standardized list can be localized. So the region in an industry can be displayed in the viewer's language. Better search for philanthropies in the state of Washington can match this profile because the list of regions can encode the fact that Seattle is in Washington, which is not apparent from the string. Greatest Center Arena. Whether you store an ID or a text string is a question of duplication. When you use an ID, the information that is meaningful to humans, such as the word philanthropy, is stored in only one place, and everything that refers to it uses an ID, which only has one meaning within the database. When you store the text directly, you are duplicating the human meaningful information in every record that uses it. The advantages of using an ID is that because it has no meaning to humans, never need to change. The ID can remain the same even if the information it identifies changes. Anything that is meaningful to human may need to change sometime in the future. And if that information is duplicated, all the redundant copies needs to be updated. That incurs write overhead and risk inconsistency, where some copies of the information are updated but others aren't. Removing such duplication is the key idea behind normalization in databases. Database administrators and developers love to argue about normalization and denormalization, but we will suspend suspend judgment for now. In part 3 of this book, we will return to the topic and explore systematic ways of dealing with caching, the normalization, and the derived data. Unfortunately, normalizing this data requires many to one relationships. Many people live in one particular region. Many people work in one particular industry, which does not fit nicely into the document model. In relational databases, it's normal to refer to rows in other tables by ID because joins are easy. In documents databases, joins are not needed for one-to-many tree structures, and support for joins is often weak. If the database itself doesn't support joins, you have to emulate a join in application code by making multiple queries to the database. In this case, the list of regions and industry are probably small and slow changing enough that the application can simply keep them in memory. But nevertheless, the work of making the join is shifted from the database to the application code. Moreover, even if the initial version of an application fits well in a join-free document model, data has a tendency of becoming more interconnected as features are added to applications. For example, consider some changes which could make to the resume example. Organization and schools as entity. The previous description, organization, the company where the users work, and school name where they study are just strings. Perhaps they should be referenced to entities instead. Then each organization, school, or university could have its own web page with logo, newsfeed, etc. Each resume could link to the organization and school that it mentions and include the logos and other information. See figures 2, 3 for an example for LinkedIn. Recommendations. Say you want to add a new feature. One user can write a recommendation for another user. The recommendation is shown on the resume of the user who was recommended together with the name and photo of the user making the recommendation. If the recommender updates their photos, any recommendation they have written needs to reflect a new photo. Therefore, the recommendation should have a reference to the auto profile. Figure 2.4 illustrates how these new features requires many-to-many relationships. The data within each dotted rectangle can be grouped into one document, but the reference to organization, schools, and other users need to be represented as a reference and require joins when required. Are documents databases repeating history? While many-to-many relationships and joins are routinely used in relational databases, document databases and NoSQL reopen the debate on how best to represent such relationships in a database. This debate is much older than NoSQL. In fact, it goes back to the very earliest computerized database system. The most popular databases for system, the most popular databases for business data processing in the 1970s was IBM, Information Management System, originally developed for stock keeping in the Apollo space program and first commercial release in 1968. It is still in use and maintained today, running an operating system 390 on IBM mainframe. The design of IMS used a fairly simple data model called hierarchical model, which has some remarkable similarity to the JSON model used by document databases. It represents all data as a tree of record nested within records, much like the JSON structure to Figure 2.2. Like documents databases, IMS work well for one-to-many relationship, but it made many-to-many relationships difficult, and it didn't support joins. Developer had to decide whether to duplicate the normalized data or to manually resolve references from one record to another. These problems of the 1960 and 1970 were very much like the problems that developers are running into with document databases today. Various solutions were proposed to solve the limitation of the hierarchical model. The two most prominent were the relational model, which became SQL and took over the world, and the network model, which initially had a large following but eventually faded into obscurity. The great debate between these two camps lasted for much of the 1970s. Since the problem that the two models were solving is still so relevant today, it's worth briefly revisiting this debate into today's slide. The network model. The network model was standardized by a committee called the Conference on Data System Language, CODASIL, and implemented by several different databases vendors. It is also known as the CODASIL model. The CODASIL model. The CODASIL model was a generalization of the hierarchical model. In the tree structure of the hierarchical model, every record has exactly one parent. In the network model, a record could have multiple parents. For example, there could be one record for the Greater Seattle Arena region, and every user who lives in that region could be linked to it. This allows many-to-one and many-to-many relationships to be modeled. A link between records in the network model were not foreign keys, but more like pointers in a programming language, which still being stored on the disk. The only way of accessing a record was to follow a path from the root record along this chain of links. It was called an access path. In the simplest case, an access path could be like the traversal of a linked list. Start at the head of the list and look at one record at a time until you find the one you want. But in the world of many-to-many relationships, several different paths can lead to the same record, and a programmer working with the network model had to keep track of those different access paths in their head. A query in Colazzi was performed by moving a cursor through the database by iteration over the list of records and following access path. If a record had multiple parents, multiple incoming pointers from other records, the application code had to keep track of all the various relationships. Even Codasil committed members admit that this was like navigating around an dimensional data space. Although manual access path selection able to make the most efficient use of the very limited hardware capabilities in 1970s, such as tape drive, whose 6 are extremely slow. The problem was that they made the code for querying and updating the databases complicated and inflexible. With both the hierarchical and the network model, if you didn't have a path to the data you wanted, you were in a difficult situation. You could change the access path, but then you had to go through a lot of handwritten databases query code and rewrite it to handle the new access path. It was difficult to make changes to an application data model. The relational data model was what the relational model did by contrast was to lay out all the data in the open. A relational table is simply a collection of tuple rows, and this is it. There are no labyrinthine structures, no complicated access path to follow. If you want to look at the data, you can read any of or all the rows in the table, selecting those that match an arbitrary condition. You can read a particular row by designating some columns as a key and matching on those. You can insert a new row into any table without worrying about foreign key relationships to and from other tables. In a relational database, the query optimizer automatically decides which part of the query to execute in which order and which indexes to use. Those choices are effectively the access path, but the big difference is that they are made automatically by the query optimizer, not by the application developer. So we really need to think about them. If you want to query your data in a new way, you can just declare a new index, and queries will automatically use whichever index are most appropriate. You don't need to change your queries to take advantage of the new index. See also query languages for data on page 42. The relational model does made it much easier to add new features to the application. Query Optimizer for relational databases are a complicated beast, and they have consumed many years of research and development effort. But a key insight of the relational model was this: you only need to build a query optimizer once, and then all applications that use the database can benefit from it. If you don't have a query optimizer, it's easy to handcode the access path for a particular query than to write a general purpose optimizer. But the general purpose solution wins in the long run. Comparison document databases.